Welcome to This Explainer. Today, we're going to demystify the incredibly complex yet totally fascinating world of hydrogen energy. You can think of hydrogen kind of like a chameleon. In its natural state, it's a completely invisible and odorless gas. But somehow, the energy industry decided to paint it in this whole spectrum of metaphorical colors. Now, these colors aren't actually visible to the human eye. Instead, they're basically a clever coding system based entirely on the gas's origin story and its resulting carbon footprint. So let's decode that rainbow together, shall we? We'll be breaking down this entire hydrogen spectrum today. We're going to start on one end with gray hydrogen, move our way right through blue and turquoise, and finally arrive at green, purple, and yellow. Basically, we're mapping out our global journey toward a sustainable, zero-emission economy. Each of these colors represents a completely distinct production pathway, and understanding them, well, it's absolutely crucial for understanding the future of global energy. So here's our roadmap for today. First, we'll cover the hydrogen color spectrum. Then we'll look at the status quo, which is gray. Next up is the transition with blue and turquoise, followed by zero emissions with green. After that, we'll check out solar and nuclear, meaning yellow and purple. And finally, we'll tie it all together with the sustainable energy future. All right, let's jump right into Section 1, the hydrogen color spectrum. Which brings us to Section 2, the status quo, which is gray hydrogen. To understand exactly where we're going, we really have to know our baseline. Right now, gray hydrogen is heavily reliant on fossil fuels, specifically natural gas, or methane. It is by far the most common and cheapest method of producing hydrogen today. Basically, natural gas is fed into a high-temperature system where it reacts with steam and a catalyst. This is a process called steam methane reforming, or SMR. Through a series of chemical reactions, including a water-gas shift, it successfully separates out high-purity hydrogen for industrial use. But there's a huge catch. Unfortunately, this process releases a massive byproduct straight into the atmosphere, carbon dioxide. And that brings us to the real environmental cost of this current standard. Get this. For every single kilogram of gray hydrogen produced, a staggering 9 to 11 kilograms of CO2 is emitted right into the air. When you think about the millions of tons of hydrogen used globally every single year for things like oil refining and ammonia production, well, that 9 to 11 kilogram ratio creates an absolute monster of a carbon footprint. Gray hydrogen might be reliable and cheap, but that emission rate is exactly why the energy sector is desperately looking for alternatives. So how do we fix it? Let's get into Section 3, the transition, featuring blue and turquoise hydrogen. Let's start with blue hydrogen. At the beginning of the process, it's practically identical to gray. It uses the exact same natural gas supply and that same steam methane reforming infrastructure. But the real game changer is what happens at the very end of the line. Instead of venting all that carbon dioxide into the sky, blue hydrogen facilities add CCUS. That stands for Carbon Capture, Utilization, and Storage Technology. They literally separate the CO2, compress it, and transport it to be injected deep underground into suitable geological formations for permanent storage. By doing this, blue hydrogen captures up to 90% of those harmful CO2 emissions. It offers a highly scalable and reliable transition solution using the infrastructure we already have built. But honestly, seeing how we handle the carbon in blue hydrogen raises a totally fascinating question. Instead of going through all the hassle of capturing carbon as this bulky gas and pumping it underground, what if we could somehow transform that carbon into something solid, stable, and actually commercially useful? Well, enter turquoise hydrogen. Instead of using steam, this pathway takes that same natural gas and puts it through a process called methane pyrolysis. This is a thermal cracking process that uses intense heat. The methane molecule is quite literally split right down the middle into pure hydrogen gas and solid carbon. And here's the best part. If the high-temperature heat needed for this pyrolysis is powered by renewable electricity, the entire process results in zero direct CO2 emissions. That's exactly what makes turquoise hydrogen so incredibly exciting. It's what we call a dual benefit technology. Not only do we get clean hydrogen, but we also collect high-purity solid carbon as a super valuable byproduct. This is helping to build an entirely new parallel market known as the solid carbon economy. That solid carbon, it can be used as carbon black for manufacturing tires, it can be processed into graphene and graphite for high-tech batteries, or it can even be used as a super durable additive in construction materials. We're literally taking a waste product that would otherwise heat up the planet and turning it into a foundational material for modern manufacturing. How cool is that?
Let's keep moving. Section 4, zero emissions, which means we're talking about green hydrogen. To really wrap your head around green hydrogen, you absolutely have to understand its core technology, electrolysis. With this, we're totally ditching the methane. We're simply taking purified water, H2O, and passing a strong, stable, direct electrical current right through it, inside an electrolysis stack. This electrical charge literally forces the water molecules to split apart. That leaves us with high-purity hydrogen gas on one side and pure, breathable oxygen on the other. That's really it. Water and electricity go in, hydrogen and oxygen come out. But what specifically makes this process green? Well, it's 100% about the power source. A green electrolysis plant is powered entirely by renewable energy, mostly sourced from wind and solar farms. Because the electricity is generated without burning any fossil fuels, and the only raw material is water, there are absolutely zero direct or indirect CO2 emissions produced here. None. The only byproduct released into the atmosphere is oxygen. This represents the ultimate ultra-low carbon energy path, basically leveraging our growing green power grid to create a truly sustainable circular fuel. Now, let's explore a couple of variations in Section 5, solar and nuclear, which give us yellow and purple hydrogen. Once you understand the magic of electrolysis, the rest of the hydrogen spectrum is just a rapid-fire variation of power sources. The core setup, the water purification, the high-temperature electrolysis stacks, the oxygen capture, and the hydrogen output, they're all essentially identical to green hydrogen. The distinct difference lies entirely in where that initial electricity is actually coming from. Let's break those energy inputs down. Yellow hydrogen is produced via electrolysis powered exclusively by on-site or dedicated photovoltaic solar panels. It's a fantastic localized solution, especially perfect for sun-rich regions, harnessing the planet's most abundant energy resource. Purple hydrogen, on the other hand, is powered entirely by nuclear energy. It uses the zero-carbon electricity and sometimes even the intense heat from an on-site nuclear reactor to drive the electrolysis. So while yellow gives us a great decentralized, localized solar path, purple provides incredible high-capacity 24/7 reliability for regions where intermittent renewables like wind and solar might be a bit constrained. And the best part? Both of them result in zero direct CO2 emissions. Which brings us to our final topic, Section 6, the sustainable energy future. So we've gone through all of the chemistry, the different colors, and the production plants. But why does all of this actually matter for our infrastructure and our future? Well, the world is investing billions into decoding this hydrogen rainbow to decarbonize massive, hard-to-abate industries. Think about heavy-duty transport like trucks and ships that are just way too heavy to run on standard electric batteries. Then you have oil refining, chemical manufacturing, and even zero-emission steel production. Agriculture relies heavily on ammonia and fertilizer production, which, right now, uses highly polluting gray hydrogen. By swapping out that gray hydrogen with blue, turquoise, green, yellow, or purple in these massive industrial applications, clean hydrogen becomes the absolute key to decarbonizing our world and building a truly circular energy economy. It all comes back to this one central idea: cleaner today, greener tomorrow. We have to be realistic here. We're in a transition period. We can't just snap our fingers and go 100% green overnight. Instead, we use highly scalable solutions like blue and turquoise hydrogen as practical, immediate pathways to drastically lower our emissions today. They basically act as a bridge, giving us the time to build the massive pipelines, storage tanks, and industrial infrastructure required for that 100% green, zero-emission tomorrow we are all aiming for. It's definitely a complex transition, but an absolutely necessary one. And depending on where you live, whether you have abundant sunshine, high wind capacity, existing nuclear infrastructure, or deep geological storage, your region's path to clean energy might look entirely different from someone else's. So I'll leave you with this final thought to ponder as we watch the incredible evolution of the global energy grid. As our economy transitions away from that heavy, gray baseline, which color of the hydrogen rainbow is going to power your community's future? Thanks so much for joining me on this explainer, and keep asking the big questions.